If I told you a plastic fragment could leave a bottle, cross an ocean, hitch a ride on the wind, slip into a glass of water, and possibly end up inside your body, would you ask the obvious question? Not, is it gross? But what does everywhere actually mean for me? It's January. The kind of cold that makes your thoughts feel sharp. You're on a shoreline that looks clean, gray water, pale sky, wind combing the surface into tight, nervous waves. The beach is mostly empty. There's a thermos on a rock beside you, warm in your hands, a small human defiance against the season. And you do the most ordinary, ancient rituals. You breathe. You drink. Later you'll eat. The world goes into you, and you go into the world. That's not poetry, that's physiology. Now here's the unsettling upgrade that only the modern era gets to experience. Our instruments have become sensitive enough to find traces of our own inventions at scales that would have sounded like science fiction 2 generations ago. Not trash. Not litter. Fragments so small they don't behave like the objects we recognize. They behave like travelers, like dust, like a strange new kind of sediment that our planet is learning to circulate. So today, you and I are going to run an audit. Not a panic. Not a sermon. An audit. We'll take one question seriously. If microplastics are everywhere, is ubiquity the same thing as injury? To make that question real, we need a character. Not a statistic. Not a headline. One particle. One traveler. Imagine it, a shard of polymer, rough-edged, no bigger than a grain of sand, maybe much smaller, blue-gray, almost pretty if you didn't know its origin story. If you want, give it a name. I'll call it Pax. Not because it's peaceful. Because it's everywhere, like a quiet agreement our civilization accidentally signed. Pax begins as an object with a purpose. Packaging. Fabric. A tire. A bottle cap. A coating. Something designed to resist time. And then time wins anyway, just not in the way we expect. It doesn't vanish. It multiplies. Before we follow Pax, we need rules, because modern science, at its best, is a disciplined way to keep ourselves from fooling ourselves. We're going to separate 3 things that get tangled online and in our own minds. First, how these particles move. The conveyor belts. The physics. Second, where they end up. The map. The destinations. Third, what counts as evidence of harm. Not vibes. Not found in. Actual mechanisms, doses, and biological responses. Keep that separation in your pocket, because it's the difference between being informed and being overwhelmed. Now, what does microplastic even mean? If you've heard the word 1,000 times, you might assume it's a single thing. It isn't. It's a category, like saying insects or clouds. The label hides diversity. In many scientific contexts, microplastics means plastic pieces smaller than 5 millimeters. That's surprisingly big. That's the size of a sesame seed, a pencil eraser shaving, a glitter speck. And a lot of what gets called microplastic is far smaller, tens of micrometers, like the width of a human hair, down to the edge of what light can even resolve clearly. Then there are nanoplastics, smaller still. Depending on the definition, we're talking below 1 micrometer, sometimes below 100 nanometers. That's the scale where particles start acting less like tiny objects and more like restless molecules wearing a solid disguise. And here's a key distinction that changes the story: detection versus quantification. Detection is like hearing a faint melody through a wall. You know something is there. Quantification is identifying the instrument, the song, and the volume, and being sure it wasn't your own headphones bleeding sound into the room. So when someone says, "It's in your blood," the only honest response is, what exactly was measured, how was it measured, and how do we know it wasn't contamination? Okay. Thermos still warm. Wind still cold. Let's follow Pax. Picture a river mouth where fresh water meets the sea. The water isn't just water, it's a moving library of everything upstream: soil, pollen, industrial residue, microscopic life, and now, polymer fragments. You can almost see the boundary where the current changes its mind. If we had dye, we could paint the flow and watch it stretch into a plume. This is where the first conveyor belt grabs packs, advection. That's a technical word that just means bulk flow. The river carries things the way a moving sidewalk carries people, whether they intended to travel or not. Packs doesn't need to swim. It needs to exist. But the ocean isn't a bathtub. It's a living, layered engine, temperature gradients, salinity gradients, currents that braid and unbraid, storms that punch the surface and stir what was settled. Now comes diffusion. In everyday language, spreading. Not because anything chooses to spread, but because randomness plus time equals dispersion. Imagine a drop of ink in water. It doesn't stay politely together. It explores the available space. Packs explores too. And then turbulence, chaotic mixing. The ocean's version of a crowded city intersection with no traffic lights, except the cars are vortices and the pedestrians are molecules and fragments. Turbulence is why a plastic fragment can move vertically, not just horizontally. It can be kicked down, pulled up, trapped in swirling eddies like little blue prisons of motion. Now here's where the plot twists: density. Some plastics are less dense than seawater and should float. Others should sink. Sounds simple, until biology enters the scene like a slow, inevitable graffiti artist. Within days to weeks, packs can become coated in biofilm, microbes, algae, tiny organisms building a living skin. This is called biofouling, and it changes packs' identity. It's like a person putting on a heavy coat. Suddenly the same body moves differently through the world. A particle that should have floated can sink. A fragment that should have been inert now carries a microbial community. So the ocean doesn't just transport microplastics. It transforms them. Sunlight breaks chemical bonds, photodegradation. Waves abrade edges, mechanical weathering. Temperature cycles stress the polymer. A bottle doesn't disappear, it becomes a crowd. A single object becomes a population of fragments, each with its own fate. Ask yourself something uncomfortable. If one bottle becomes a crowd, what does that do to the meaning of cleanup? Now, as we follow packs farther offshore, the water changes color, the horizon opens up, and the scale of the system becomes humbling. This is where people like to say, the ocean is vast, it will dilute it. But dilution is not disappearance. Dilution just spreads the problem into places we don't look often enough. And then, sea spray. Watch a wave collapse. That burst of white isn't just foam. It's a factory of aerosols, tiny droplets launched into the air by the violence of bursting bubbles. When bubbles pop, they fling microscopic bits of what's in the surface layer into the atmosphere. Salt, organic matter, and under the right conditions, microplastic fragments and fibers. So packs can leave the ocean without a ship. Wind becomes another conveyor belt. And suddenly, what felt like a marine pollution problem becomes an air problem. Now we shift scenes. You're no longer on the lonely shoreline. You're in a city street. You feel the grit in winter air. A bus sighs at a stoplight. And beneath this ordinary soundscape, there's a less visible one: tire wear. Every rotation of a tire is friction made tangible. A tire is not just rubber, it's a complex composite, often including synthetic polymers and additives. And it sheds. Textiles shed too. Every wash. Every tumble in a dryer. Every time fabric rubs against fabric. Fibers detach, drift, settle, rise again when a door closes or someone sits on a couch. The indoors, where many of us spend most of our lives, can be a concentrated environment for fibers and dust. Pause here and ask, if you inhale air thousands of times a day, what matters more, an occasional dramatic exposure or a quiet, chronic background? Now let's enter a kitchen. Not a lab kitchen. A real one. The hum of a refrigerator. A cutting board. Tap water running, catching the light. If microplastics are going to become personal, they'll become personal here, where you don't feel like you're making environmental choices. You feel like you're making dinner. Routes of exposure aren't all equal. Some are well supported by evidence, some are plausible but overclaimed. Seafood can contain microplastics, especially filter feeders, and especially in certain environments. Salt has been measured with microplastic contamination in some studies. Bottled beverages have repeatedly come up in measurements, though methods vary and the numbers can swing widely. Packaging abrasion can contribute. Dust can settle on food. Cutting and heating plastics can accelerate shedding. But an audit means we don't just list pathways like a horror montage. We ask, what's the dose? How often? What size? What polymer? How confident are we? Here's what we can say with high confidence, without inflating the case. Microplastics are widespread in marine environments, sediments, and many urban airsheds. They fragment and weather, their surface chemistry changes. They can carry additives from manufacturing, and they can absorb other pollutants from the environment like a sponge picking up whatever is in the water. Humans are exposed through ingestion and inhalation, and with modern analytical methods, particles are detectable in some human samples. But detectable is a treacherous word. Because what comes next, the leap from present to dangerous, is where certainty gets expensive. So we walk into the lab. The fluorescent lights are too bright, the benches are crowded with glassware, filters, tweezers, and instruments that look like they were designed by people who speak in spectra. This is the edge of understanding, where you can feel how hard it is to turn a global anxiety into a measurable claim. And the question changes. It's no longer, where are they? It becomes, what do they do? Let's run a stress test on our mental model. Imagine packs approaching your lungs. Your airways branch like an upside-down tree. Large particles get trapped earlier, caught in mucus, swept up by cilia, expelled. It's not a passive pipe, it's a self-cleaning system. But smaller particles can travel deeper, into regions where clearance is slower and biology is more delicate. Now imagine packs in your gut. It meets a mucus layer that's part barrier, part negotiation. Your intestine is not a simple tube, it's a living interface between you and not you. Most particles should pass through without crossing into tissues. But size matters. Surface chemistry matters. Shape matters. A smooth bead is not the same as a jagged fragment, or a long fiber. At this point, a reasonable person asks, can these particles cross barriers? Can they enter blood? Can they reach organs? The cautious answer is, some studies have reported microplastics in human blood and tissues, using advanced spectroscopy or mass spectrometry approaches. But the field fights constant battles against contamination, fibers from lab coats, airborne dust, plastic tools, even the sampling containers. When you're hunting for tiny fragments, the world itself tries to sabotage you with background noise. And the smaller the particle gets, the harder it becomes to identify unambiguously. You can detect a signal that looks like a polymer, but proving what it is, how much of it is there, and whether it came from the sample or the room, those are not trivial steps. So when you see a headline, don't just ask, is it true? Ask, what was the detection limit? What controls did they use? How did they prevent contamination? And can other labs reproduce it? Now, the harm claims. What do we actually know? In cell cultures and animal models, certain microplastics at certain doses can trigger inflammation signals and oxidative stress, an imbalance where reactive molecules outpace the body's defenses, like sparks landing faster than you can stomp them out. There's potential for physical irritation, especially with fibers or jagged fragments. Additives, plasticizers, stabilizers, colorants, can have biological effects on their own, and plastics can carry other chemicals on their surfaces. But an audit means we don't stop at can. We ask, does, at realistic doses, over realistic times, in real humans? This is where the gaps matter. We still need clearer estimates of real-world human doses over years. We need standardized methods so labs can compare results without arguing over definitions. We need longitudinal studies, following people over time, to link exposure patterns with health outcomes. And we need mechanisms that connect particle properties to biological responses in a way that survives replication and skepticism. If you feel the tension right now, good. That tension is honest science. Because here's the paradox. The better our microscopes and mass spectrometers get, the more everywhere becomes true, without automatically making harm more certain. Improved detection is like turning up the lights in a room. You see more dust. The dust may have been there all along, but now your awareness accelerates faster than your understanding. Another subtle trap, microplastics aren't one thing. A pet fiber from clothing behaves differently than a tire wear fragment. Polystyrene beads behave differently than polyethylene films. Size, shape, polymer type, surface weathering, and chemical hitchhikers all change the interaction with biology. So the story can't be a binary of safe versus toxic. It becomes a four-dimensional problem: dose, size, chemistry, and time. And our datasets, right now, are still being stitched together like a quilt where some squares are detailed and others are blank fabric waiting for evidence. This is the moment where something clicks. You stop asking for a single verdict and start asking for a map of conditions. You realize the most responsible question isn't, "Is it killing me?" It's, "Under what conditions does it matter, and what can we do while we learn?" So what does the audit conclude so far? Credible concern exists, especially for smaller particles and for chronic exposure, yet the magnitude of human health risk is still being quantified. The strongest near-term stance is precaution paired with better science. Reduce exposure where it's feasible, standardize measurement methods, and control sources upstream so we're not trying to filter an ocean with a spoon. Now let's zoom out. Dawn is coming up over the same water from the beginning, January calm now, the surface softening into silver. Microplastics become a mirror. They show us something about our world that's bigger than any one particle. The planet remembers our materials choices. Not metaphorically. Physically. In sediments. In air. In bodies. In the quiet archives of ice and deep-sea mud. And there's a philosophical takeaway that matters in 2026 more than ever. Modern life creates signals our instruments can detect before our biology and policy can interpret them. There's a lag between detection and meaning. That lag is the new frontier of public science, and it's where misinformation thrives if we don't learn to think carefully together. So let's talk agency, without false certainty. If you want the highest leverage interventions, they're upstream. Reduce tire wear emissions through road design, vehicle weight, and tire technology. Reduce textile shedding through fabric engineering and washing filtration. Prevent packaging loss. Upgrade wastewater and stormwater filtration where it makes sense. Enforce industrial pellet handling so raw plastic doesn't leak at the source. These are systems problems, and that's good news, because systems can be changed. Personal exposure reduction is real but incremental. Think of it like lowering background noise, not building a bunker. Ventilate when you can. Wet dust instead of dry dusting. Consider HEPA filtration in high-dust homes. Be mindful with heating plastics. Heat accelerates shedding and chemical migration. Choose lower-shedding textiles when practical. Make food storage choices that reduce contact with stressed plastics. None of this is about purity. It's about small advantages compounded over years. And here's the scientific literacy point I want you to keep: found in is the beginning of a question, not the end of it. Presence is a clue. Risk is a conclusion. The space between them is where science lives. Now return to PAX, our single traveler. It hasn't stopped. It never really stops. It's in motion through currents and wind, through rooms and lungs and filters, through data tables and headlines, through your attention right now. So here's the synthesis: clean and honest, microplastics move through powerful planetary conveyor belts, rivers, oceans, air. They transform as they travel. We are exposed through ingestion and inhalation. We can detect them in environments with high confidence, and in some human samples with growing evidence. But translating everywhere into this specific harm at this specific dose is still a scientific frontier, complicated by particle diversity, measurement limits, and the slow mathematics of chronic exposure. And now, a thought experiment to take with you: imagine two futures. In one, our instruments keep improving, and we keep discovering new traces in new places, but we never build the cultural skill to interpret detection without panic. In the other, we treat detection like a compass, not a verdict, and we build standards, reduce sources, and design materials as if the planet is not an infinite sink but a shared bloodstream. Which future feels more like adulthood? The next great question, the one that opens the next door, is this: if our civilization can seed the planet with particles small enough to enter the intimate spaces of biology, what other invisible byproducts are we already making that we simply haven't learned to measure yet? If you want to keep going, click the video on the end screen, because it picks up from here and pushes this same audit mindset into the next frontier. And I want your answer in the comments, simple and personal. What's one place you suspect microplastics show up in your daily life? Air, water, food, clothing, or something else? And if you subscribe, do it for a clear reason. This channel is where we separate signals from noise, where we don't trade fear for clicks, we trade confusion for understanding, one careful investigation at a time.